All right, so part 5 of chapter 7, entropy. This is a long chapter. So in this section, we are actually going to talk about a very interesting topic, and entropy balance. So entropy balance is similar to energy balance. So you remember that, so probably we are better off if I start from this diagram here. This is a very good picture. So in this picture, we do see a system and the surrounding, and with arrows we see energy in, entropy in, energy out, entropy out. So we regard entropy in a very similar way that we regarded energy. So for a system, either open or closed, we said that energy in minus energy out in general is equal to delta E of the system. So if it was like in the case of a control volume, then there was contribution of energy in and energy out from the inlets and outlets, but this equation always holds. This is energy balance or conservation of energy. How about entropy? For entropy, we can also argue that entropy comes in, entropy goes out, and also in this case, entropy can be generated in the system. In the case of energy, we didn't claim that. In the case of energy, energy cannot be generated. It can be converted from one form to the other. So for entropy balance, the balance equation is a little bit different. We say that entropy in minus entropy out plus entropy generation is equal to the change of the entropy of the system. So that's the issue that we have with the entropy. Entropy is, continuously generated in the universe on the earth. That's why we mentioned before that this entropy generation can result in global warming because it results in, higher temperatures. So if we want to formulate it, therefore, we say that total entropy entrance minus total entropy leaving plus total entropy generated is equal to the change of the entropy of the system. This entropy generation, if you have watched the videos and studied the book carefully, the entropy generation is because of the irreversibilities in the system. If the processes that occur are fully reversible, then entropy generation will be zero. But if there is friction effect, there is sudden expansion, there is heat transfer with a finite temperature difference, and this kind of things, which are all of them, or they are in general present in real world processes, then we do have entropy generation. So in this form that you see, it is not a rate equation, so it doesn't have dot on it, or it doesn't say whether the system is closed or open. So for now it's very general, and then later we will specify it for a particular system or control volume or type of processes such as a steady flow. This delta S of the system that you see here is similar to delta E of the system. It is equal to the final entropy minus the initial entropy. So it's equal to S final minus S initial, or simply S2 minus S1. So this is our key equation here, and we are going to use it and apply it for some particular cases. All right, so we said that entropy in minus entropy out plus entropy generation is equal to the change of the entropy of the system. Now the question is that what are the mechanisms of entropy in and entropy out? So there are multiple mechanisms. One obvious one is by heat transfer, and because by definition entropy difference or entropy generated between process 1 to 2 is equal to the integral of delta Q over T for a internally reversible process. So entropy therefore transferred as a result of heat transfer is equal to the integral of delta Q over T between state 1 and state 2. So this integral may be actually simplified or converted to a summation, the summation of all heat transfers, and for each heat transfer we may be able to define an associated temperature, so that's why we can show it as Qk over Tk. So this means that, for instance, if a system is exchanging heat with multiple reservoirs, and from each reservoir Q amount is transferred, what would be the associated temperature, what would be the temperature associated with that particular reservoir? So that's what it means. So this T temperature is tightly connected with that Q. So to give you an example, let's say we are looking at this system here, and let's say that the 500 kilojoules of heat, well, 500 kilojoules of energy crosses the boundaries in the form of heat and enters the system. So now we do need a temperature to associate to this heat transfer in order to be able to calculate the entropy transfer, because entropy is Q divided by a temperature. So now we go ahead and assign that this temperature to the boundary. Because heat transfer occurs at the boundaries, we do need to know the temperature at the boundaries. So if the temperature at the boundaries is 400 Kelvin, then the entropy transfer to the system is equal to heat divided 500 divided by 400. All right, so how about work? Does work transfer like transfers entropy? The answer is no. So entropy of work is 0. For instance, if we do have a shaft crossing the boundaries of the system, so as the shaft crosses the boundaries, there is no entropy transfer to the system just because of the shaft. However, because of the impellers, because of the rotation of these impellers inside of that system, for instance, if this is a fan, something like that, then that mechanical work of the fan may be converted to, but because of friction, it may be converted to heat, and then we can say that yes, the work has been converted to heat, and therefore entropy has increased because of this work process. However, the work itself does not transfer entropy. But the problem is that sometimes the work is wasted to heat, and that is the process where transfers and generates entropy. So we can say that no entropy accompanies work as it crosses the system boundary, but entropy may be generated within the system as work is dissipated into a less useful form of energy, which is like heat. So entropy is transferred therefore by heat transfer. So anytime that we have heat transfer, we have entropy transfer as well. And work does not transfer entropy, by itself. What else? Entropy can be transferred by mass flow. And this happens in the case of an open system or a control volume. So consider this control volume here with an inlet here. So mass flow rate is m dot, similar to the previous chapters on the first law. So the energy which is coming in this case is equal to m dot times h if we neglect the kinetic and the potential energy. Similarly, if we multiply m dot by S, the entropy. M dot S is the entropy which is transferred to the system or to this control volume. So entropy can be transferred by heat, not by work, and also can be transferred by mass itself, because mass carries not only energy, it carries entropy as well. So that's why when you look at the air tables, steam tables, entropy is listed the same way that enthalpy and internal energy are listed. So now that we know the ways of entropy transfer, we can go ahead and formulate the concept or the principle of conservation of entropy for a closed system for now. So we said that entropy in minus entropy out plus entropy generation is equal to delta E, delta S of the system. So entropy in minus entropy out plus entropy generation. So that's the entropy generation term. Then how about the entropy in and entropy out? So if we do have a closed system, so entropy cannot come in by mass because it's a closed system. So entropy can come to the system only because of heat transfer. And therefore, it may come from multiple, for instance, reservoirs, so it can be more than one. So therefore, we write the entropy transfer coming to the system as the sum of Qk over Tk. So this Q may be associated with a temperature, let's say T1. So, and the other Q may be associated with another temperature like T2. So the temperature at the boundaries of each particular heat transfer. So therefore, this can have an index X Q1 T1 and Q2 T2. So this is for entropy transfer to the system. So now if we want to consider the surrounding as well, the entire surrounding, so we see that we can go ahead and write the same equation but for the surrounding. So for the surrounding, we still can have the similar terms. However, the heat which is transferred to the system is removed from the surrounding. Therefore, it's like that entropy is removed from the surrounding. So for the surrounding, this term Q here would become negative because the surrounding is actually losing heat. So for the surrounding, this entropy the transfer term by heat becomes negative, and it would have its own entropy generation and then the change in the entropy of the surrounding. So if we add these two together, the entropy of the system and surroundings together, then the contribution because of heat transfer will cancel out, because for this one of them is positive, for the other one is negative. What remains is just entropy generation in the system and surrounding together, which is equal to a change in the entropy of the system plus the entropy of the surroundings. So that's why when we consider everything in this world and the surrounding as the entire universe. So the entire universe would be all of the small systems and the surroundings. So the entire universe would be like become the system plus the surroundings. So in the entire universe, what happens is some net amount of entropy generation, which is positive. So the heat transfer in the entire universe is all internally. So entropy is transferred, is removed from one part, added to another part, for instance, by heat transfer. But the irreversibilities cannot be eliminated, and those irreversibilities in the entire universe results in entropy generation in the system plus the surrounding. For a control volume, which is an open system, we do have entropy transfer, but still by heat transfer, crossing the boundaries. No entropy transfer by work, so we don't have to worry about it. And then we still have entropy generation because of irreversibilities as usual. Then we have entropy coming in from the inlets, sum of MISI, if there are multiple inlets, and entropy can leave the system from the outlets, MESE. And the sum of this is equal to the change of the entropy of the control volume. So this is the general open system or control volume, not for a particular process. If we want to apply it for a steady flow problem, then we should show these equations in the rate form. So we need to put dot on top of all of them. So if we do so, this Q becomes Q dot, M's become M dot, S generation becomes S dot generation, and for a steady flow, this term S2 minus S1 of control volume does not change because it's a steady flow. So the above equation is converted to this form. If we rearrange, it's still the same as above. It's in the rate form and it's been rearranged. So we can express S dot generation equal to entropy in from the inlet, entropy out from the outlets minus entropy in from the inlets minus the entropy transfer from the system through heat transfer process. If we just have one single inlet and one single outlet, then because of the conservation of mass, m dot in is equal to m dot out. So the above equation is simplified to this form. S dot generation is m dot SE minus SI minus the sum of the Q dot K over TK. And even though we do see a lot of negative signs here, minus, minus, but this entropy generation must be positive. If you do a calculation, do a problem and see entropy generation is negative, so you have done it wrong. And here is the visual observation and understanding of the control volume. So entropy coming in from the inlets, entropy going out from the outlets, heat transfer, that's the temperature associated with this heat transfer, and that's the entropy balance for a closed system. Sorry, for this open system. So some examples. So entropy balance for a throttling process like a throttling valve or capillary tubes, that's where pressure drops significantly. If we show it on a TS diagram, from the energy balance or first law, you remember this process. So energy, so if you want to write the first law, energy in dot in is equal to E dot out. Oh my god, it's so hard to do it by the mouse. Oops, I messed it up. So E dot in equal to E dot out. So the energy which is coming in, if we neglect the kinetic and potential energies, energy coming in is only entropy per unit mass, and energy going out, the energy is enthalpy per unit mass, and the energy going out is H2 at the exit. So that's the energy balance for a throttling process. So it's an H or enthalpy constant process. On a TS diagram, enthalpy constant process is like this line. This is of course not obvious to you that, okay, how come enthalpy constant should have this form, but accept it, for now. So this is constant entropy line, in a throttling process, and this is the dome for two-phase mixture. And here is like for a gas, for instance. So if we want to apply the principle of entropy balance, entropy in minus entropy out plus entropy generation is equal to delta S of the system. This is for a steady process, so this term is 0. Everything is in the rate form, S dot in minus S dot out plus S dot generation. So S dot in this throttling process is equal to M dot S1, entropy coming in to this, so this control volume is very small, so you are just looking at this part. This is your control volume, right? M dot S1 is coming in, M dot S2 is going out, plus S dot generation, and then on the right side equal to 0. So entropy, if you rearrange, S dot generation is equal to M dot S2 minus S1. If we look at the TS diagram, so you see for this process, this is S2, entropy at the exit, S1, entropy at the inlet. So S2 is of course larger than S1 because entropy generation should be positive. So the entropy generated is M dot S2 minus S1. So this throttling device is actually an entropy generator device because it breaks down the pressure. So you see pressure here is 7 megapascals and then it drops to 3 megapascals at the exit. So you expect to have generated a lot of entropy through a throttling process. It's like a throttling process, it generates entropy. So this slide is quite interesting, entropy generation associated with heat transfer process. It is a quite complex topic and not very easy to understand. So first of all, we said that entropy, so based on the definition of entropy, entropy was like ds equal to delta Q over T for an internally reversible process. So that's the definition of entropy. So now if we look at this system and the surrounding, so the system has a temperature, the surrounding has its own temperature. If we want a heat transfer to occur from the system to the surrounding, so the temperature of the system must be higher than the temperature of the surrounding. So entropy transfer for the system by definition is Q over temperature of the system. So Q over T system. But the temperature of the surroundings is lower than the temperature of the system. So the same amount of Q, which is crossing the boundaries, will generate more entropy in the surrounding because Q divided by T surrounding is larger than Q of T system. Because T surrounding is smaller than T system, but Q's are the same. So what happens during this process? So you see that entropy which has left the system is like this amount, and entropy which has been added to the surrounding is larger. So what happened? So what happens is as follows. Because of a temperature difference, a finite temperature difference between T sys and T surrounding, we do have entropy generation in this process. This is an irreversibility because of a finite temperature difference. So the difference between Q over T surroundings and Q over T sys is the entropy generation due to heat transfer. So heat transfer does two things. So first of all, the definition of entropy is based on heat transfer itself. So when we do have heat transfer, we do generate entropy. So we generate delta S. In addition, if the heat transfer is associated with a finite temperature difference associated with a delta T that you see here, which is not non-zero, so therefore this process is not reversible, and as a result some entropy will be also generated because of this temperature difference. So that's why Q over T sys plus entropy generation is equal to Q over T surrounding. So in this case, in A, the wall thickness was neglected, so we saw a sudden drop in the temperature. But if you want to consider the thickness of the wall, then the temperature will, if it's like a linear wall, the temperature will drop linearly. You will see it in heat transfer. So during this, therefore, entropy generation will still occur, but in a gradual way. And in case C, you will see that, for instance, if you consider the presence of air outside of the wall and inside of the wall, then the temperature profile will be further modified because of the convection outside and inside. And then in the wall, we only have conduction. During conduction, the temperature profile is linear. During convection, it is non-linear, as you see. So during this process, still, we do see Q over T system and Q over T surroundings at the final values. And then in between, gradually some entropy is generated as we move from the higher temperature inside the room to the lower temperature outside the room. So this was a very interesting and important slide, graphical representation of entropy generation during a heat transfer process through a finite temperature difference. Okay, so this brings us to the end of this chapter, at least the lecture part. Now we're going to go ahead and do a couple of problems. So actually multiple problems in order to clarify the use of everything that we talked about in this lecture. So we are able to do a large number of problems with different characteristics based on what we have learned. And we haven't got a chance to go over problems yet. So I wanted to finish all of the materials which were related. Now we do have the chance to go over and do multiple problems, probably in 2 or 3 additional lectures that we will follow. Thank you for your attention.